our energy systems and play a key role in reducing carbon emissions across industries. Or we can say that's in other uses also in the transportations and other stuffs. So imagine a world where we can power everything from car to factories without emitting a single gram of carbon. So this is the vision behind green hydrogen, a clean, renewable energy sources and could reshape our future. So this climate change, so we have to back to our good climates and drive us towards a sustainable energy economy. So the goal of energy transitions is underway, but as we split away from fossil fuel, one critical question remains: how do we store and transport energy sustainably? So green hydrogen offers as an answer to us. And today presentations, I will exploring about the green hydrogens and their generation process, storage, transportations. So world is facing a climate crisis because that every time we heard that in the news, global warmings and other stuffs. So we need bold solution to reduce carbon emissions. So green hydrogen could play a vital role as a studies shows it has the potential to cut global CO2 emissions by up to 6 gigaton annually. So that's the huge amount we can say. So green hydrogen is more than just a buzzy word. It's a game-changing technology that holds the potential and revolutionize the way we generate, store, and use energy. In this presentation, I will tell you some detail about hydrogen, like say the generation, storage, and transportation. So this we will go ahead in my slides. So what if we could create a zero emission fuel that could power industries, vehicles, even homes? So the answer lies in green hydrogen, a powerful sustainable energy sources that is rapidly gaining momentum. So let's dive into why it's one of the most promising solutions for decarbonization future. So just as my topic, so why, what is green hydrogen and why we call the green to that hydrogen? So green hydrogen refers to hydrogen that is producing using renewable energy sources such as wind, solar, hydroelectric power. So I am just telling that our topic more in the details. So this topic. So this is the green hydrogen. So electrolysis involves using electricity to split water molecules into hydrogen and oxygen. So this is the way where we use the sustainable energy, means that the renewable energy. So there is a less, means no, zero emission of the carbon. So therefore the word is green come up over there and we call green hydrogen. So the term green is green hydrogen comes from the fact that its production process is environmentally friendly and sustainable. The key reasons it's called green includes the carbon-free productions, renewable energy we use to produce, and sustainable energy. So green hydrogen offers sustainable solutions for energy storage and decarbonizing, making it key element in efforts to reduce reliance on fossil fuels. Okay, and then come back climate change. So key benefit of the green hydrogen, that's I already say the decarbonizations, energy storage and sustainability by relying on the reliable energy. So green hydrogen contributes to a sustainable clean energy future. So in summary, the green hydrogen is considered a key player in the global transition to clean energy because it produces without emitting greenhouse gases, making it an essential component of decarbonization strategies. So that's the point. And sorry, now I just go on this. My next is that the agenda. So here I just put it the agenda. Sorry. Yeah. So there is some of the points which I highlighted here that we will discuss. Colors of hydrogens means the color coding, that the hydrogen we can describe in the color coding way, and the green hydrogen production process means how can we produce the water electrolysis process that we can use for the green hydrogen, and then the electrolyzers technology, because this electrolysis process we use the electrolyzers and the technologies, characteristics of electrolyzers, advantage, disadvantage, hydrogen storage, transportations, and one I will show that the one typical plant configurations here. So this is I am just representing here the colors of hydrogen. So this is the hydrogen color spectrum, and there I just take the picture and presenting there the different colors. So colors means there is a gray color, blue color, pink color, brown color, so many colors. And this color codings and the naming, we can say the nicknames. So therefore essential color codes or the nicknames used within the energy industry to difference between the types of hydrogens. So hydrogen is categorized into different types based on the method of its production. And these are often related to, sorry, these are referred to by their color codes. So each color represents the environmental impact of hydrogen production and technology used. I will tell you detailed breakdown of different hydrogen's color codes. So this is I'm just pressing next slide. This is in that spectrum here. This is a gray hydrogen. So what is the gray hydrogen? So gray hydrogen is produced through steam methane reforming, which involves extracting hydrogen from natural gas. So gray hydrogens derive from natural gas. So it is the most common production method today, with nearly 60% of hydrogens made in this way, as international energy agency says. This process is the most common method used to produce hydrogen. This method releases significant amount of CO2 into the atmosphere. As the carbon contained the natural gas in not captured, gray hydrogen generates significantly lower CO2 emissions than the brown version. So brown version, I will explain you in the later, because in the brown version, we use the coal as a energy source. So in a gray hydrogen is the least environmental friendly because it contributes to carbon emissions, making a fossil fuel based energy source. And here I can say that the key points, that's the cheapest from the form of hydrogens, carbon intensive, most commonly used today. So that's the key points. Now go on the blue hydrogen. So blue hydrogen is also produced through the same as a gray hydrogen. Only the difference that's we just use here carbon capture storage technology to capturing the CO2 emission produced during the hydrogen extraction process and store them underground, these carbons capturing. So CO2 emission are mitigate to some extent through this CCS. CCS means carbon capture and storage. So making the blue hydrogen cleaner than the gray hydrogen, though it still involves fossil fuels. So blue hydrogen is considered a traditional fuel while it reduces emission compared to gray hydrogen. It is still based on the natural gas. So because we are the method of blue and gray is the same, we are using the natural gas, but in the blue, what we are doing, we are using the CCS technology That is a carbon capturing technology, and we can capture the carbon, whatever the carbon that's going to the climate. So in this way, we can improve our carbon capturing capacity and improve our climate. So here, the key point of this method, this technology is what? This is a cleaner than gray hydrogen due to this CCS. So require significant investment in CCS infrastructure. So this is the key point, because there is an additional, we have to make an additional infrastructure to capturing this carbon. So that is the additional cost in this. Can still be carbon intensive depending on effectiveness of carbon capturing process. Now I just go on next one. This is turquoise hydrogen. So turquoise hydrogen gets its name because its productions process is still somewhere between gray, green and blue, not gray, green and blue. A method called methane pyrolysis, a process that use high temperature to break down methane, means that the natural gas, into hydrogen and solid carbon. The solid carbon can be stored or used in various industries, because that when we take it the hydrogen and the byproduct is the solid carbon, so that solid carbon used in the various industry for the different purpose. So such as in the manufacturing of the carbon productions, we can say. So the lateral is a critical raw material with a wide variety of industrial application, including making car tires, coatings, and the batteries. So in such companies, they require the carbon. So this carbon they can use over there. So the great advantage of this technology is that are no CO2 emissions to deal with this method. So this method produces no CO2 emission if the solid carbon is properly stored or utilized. So making it clear alternatively compared to the gray and even blue hydrogen. So we can say that this is better than these two. So pyrolysis is considered as a promising new technology for producing hydrogen with a lower environmental footprint, especially if the carbon utilized rather than released into the atmosphere. So here the key points, what we say, so lower carbon emissions, and depending on how the solid carbon is handled. And then the second, we can say that the emerging technology. So not a widespread as a SMR or electrolysis. Now, next is green hydrogen. Right now, this is our topics, and this is also the one form of the hydrogens to generate on their electricity and the process. So green hydrogen is the holy grail for policymaker, climate activity, and the energy sector. It is a made by electrolysis, a process that use electricity to split water into hydrogen and oxygen. And electricity must be provided by renewable energy. That is the main important here. If energy is your renewables, such as the solar, wind, there is a zero carbon emissions. So we say the green hydrogen. While production's volume are still low and the cost are high, around 350 projects are underway globally that could shift these economies. So green hydrogen is completely carbon free because the electricity used come from renewable sources. Meaning, renewable sources meaning that's what? No CO2 is released during its production. So therefore we say the green. So green hydrogen is considered the cleanest form of hydrogen, and it does not contribute to carbon emission. It's play a significant role in decarbonization of industries and sector like transportation, power generation, and heavy industries. And here the key points, I just say that most environmental friendly, requires abundant renewable energy for productions, and higher production cost due to need of renewable electricity and electrolysis equipment. Yellow hydrogen. So yellow hydrogen typically refers to the hydrogen made using electrolysis power by solar energy. We can say solar, or specifically the grid energy. So grid energy means what? That in a grid, we can connect both renewable as well as for our traditional method. That's we generate the electricity from our fossil fuels. So this both generating station give the power to the grid, and that if we are taking the power supply from the grid and use for this electrolysis process, so we call the yellow hydrogen. And however, it is something sometimes also used to describe electrolyzed hydrogen create form of mixed renewable and the fossil fuel power. So yellow hydrogen does not have the strict technical definition, but it typically implies the use of grid connected electricity electrolysis process. The key feature of yellow hydrogen is that is use electricity from public or national grid power grids. So the grid energy can comes from variety of the sources, including the power from renewables or non-renewable sources like coal, natural gas, nuclear. And if renewable, so we say the solar, wind, and hydro. That is the renewables come under the renewables. So a more religious traditions to cleaner renewable energy sources for electricity, yellow hydrogen could become a viable and most sustainable option if the energy grid shifted towards the decarbonization electricity, means that towards the renewable energies contributions. If maybe easier to scale up yellow hydrogen productions because it's leverage existing grid infrastructure and electrolysis technology, especially electric becomes greener. So there are challenges like the carbon footprint of the yellow hydrogen is variable and depend on energy mix of the grid. If fossil fuels dominate the grid, the hydrogen produced can be still have a significant carbon footprint. To make a yellow hydrogen more sustainable and regions with abundant renewable energy generation need to be identified, or the shares of renewables in the grid must increase. So therefore, yellow hydrogen represent the form of hydrogen that is produced through electrolysis powered by electricity grid. Its environmental impact depends on the energy mix of grids, and it's offer traditional pathway towards cleaner hydrogen productions as the grid decarbonizations. So that's the yellow. And now is brown. Brown hydrogen. Brown hydrogens, earlier we discussed, right now I just say that the coal used for this. So brown hydrogen represent the traditional process of making hydrogen. Which use either black or brown coal and producing using coal gasification, a process where coal is heated to produce hydrogen and carbon monoxide. The carbon monoxide is then further processed to produce hydrogen. So brown hydrogen is very carbon intensive, as a coal is a fossil fuel that emits large quantity of CO2 when using this process. So this one is producing CO2 as compared to the all is higher. So this is the most environmentally harmful method of hydrogen production, similar to gray hydrogen, but more polluting due to the use of coal. In 2020, around the fifth hydrogen gas was still made using coal. According to the International Energy Agency, IEA, and here we can say the key points. The most populating form of the hydrogen use a coal, which is one of the most carbon intensive fossil fuel and not commonly used due to the environmental impact. Yeah, is the last one is we can say the pink hydrogen. So pink hydrogen is similar to the green, but with one difference. The electrolysis is powered not by renewable electricity, but the nuclear energy. So, which is experienced revel as a carbon-free energy source. Because here also we can say the green energy, but why not saying that we are saying the pink? Because we are using a nuclear power, and nuclear power also has some issues about the nuclear waste. So the most commercial deal was signed in January 2022 and will see a Swedish nuclear power plant delivered pink hydrogen to industrial gas giant Linde. So Linde was their client and they do this. So hydrogen production using nuclear power is also sometimes refers to as a purple or red hydrogen. The process itself is a carbon free as a nuclear power does not emit CO2 during electricity generation. However, concern about nuclear waste and the safety persist. So pink hydrogen is considered clean in terms of emission, but the environmental debates around nuclear energy may make it less widely accepted option in some regions. So therefore, green hydrogen is more popular than the pink. The key point is the carbon free as it use nuclear energy. So potential concerns about nuclear waste and public acceptance less common than other form of hydrogen. So this is the each color of hydrogen represent a different production method with varying levels of environmental impact. So green hydrogen is the cleanest and the most sustainable options, but it is also most expensive. Other types like blue and turquoise hydrogen offer intermediate solutions with lower emissions, while gray and brown hydrogen are highly polluting as the world moves towards decarbonization. So green hydrogen is seen as a future of hydrogen production. And then here I'm just uh, preparing one this tables for hydrogen color codes based on their methods, carbon emissions, and environmental impact. So here the same things. Sorry. Yes. Here with the same things, we just specify that the green, gray, blue, turquoise, green, brown, yellow, pinks. So their production methods, their carbon emissions, how and up to what level they emit, and environmental impact also. Here we specify the same things. This is the comparison I just show is the easy to understand. Now, so green hydrogen. So green hydrogen, that is a water electrolysis process we use to generate this. So here the water electrolysis process is what? So water electrolysis process, I suppose that everyone knows because that we read this electrolysis process in our earlier school times and the college times. So electrolysis process is splitting of the water into hydrogen and oxygen using electricity in an electrolyzer cell. So cell is called a electrolyzer. So So electrolysis cell consists of the two electrode that are separated by an electrolyte. An electrolyte is a medium responsible for transporting chemical changes from one electrode to other. So this is a simple way to understand the electrolysis process. And electrolysis process, we have some based on this, we have some technologies which we are using to generate green hydrogens or hydrogen. So there are the four technologies. This is in my screen. So this is alkaline water electrolyzers. Second is AEM, anion exchange membrane, PEM, PEM. So polymer electrolyte membrane technology, and SOEC, solid oxide electrolyzer cell. So just go on that one by one to discuss about that the each technologies, how it's use and work. So alkaline water electrolysis, AWE, this alkaline electrolysis is the most mature commercial water electrolysis technology. It is established mature technology for industrial hydrogen production. The alkaline water electrolysis phenomena was first introduced by Prost Trostwick and Demand in the year 1789. After several development in the year of 1939, the first industrial large-scale alkaline water electrolyzer plant with the capacity of 10,000 normal cubic meter per hour of hydrogen production went into the operation. The alkaline water electrolyzers operates a lower temperature, 30 to 80 degrees Celsius, with the concentric alkaline solution. So moreover, in alkaline water, electrolyzers have nickel-coated stainless steel electrodes and asbestos or zinc chromium oxide-based diaphragm are used as a separator. So the alkaline water electrolysis is a favorable system designed for a large-scale applications. So AWE, alkaline water electrolyzer, is an electrochemical water splitting techniques in presence of electricity. So electrolyte solutions we used here as a alkaline solution like KOH or NOH, which helps improves the water conductivity. And electrode, the two electrode, we know that the electrolysis process will require two electrode and the electrolyte solutions. So the two electrode is anode and the cathode are placing in the electrolyte solution and are connected to the power source and provide the DC current, direct current, plus and minus, put it on the anode and minus connected to cathode. So what happened after that? So at the cathode and the negative electrode, so um, reduction reaction occurs and the hydrogen gas H2 is produced. Because that if you see in the diagram 2HO means two molecules of H2O waters and then electrons, if they are react, so they are produce the hydrogens and the hydroxide ion. So water molecules are reduced by gaining the electrons and producing the hydrogen gas and the 2OH negative, that's in the drawings, hydroxide ions. This is happens in the cathode side. And then anode side, positive electrodes, we say oxidation reaction occurs and the oxygen gas is produced. The hydroxide ions are oxide to form of oxygens gas and release electrons. So this is the shortly I described this process and then happening that the how to hydrogen generate and oxygen is generating from it. So what we do, the hydrogen is collected at cathode and oxygen is collected at anode. The hydrogen and oxygen gases are separated by the electrolyte solution. So the process is typically carried out in a divided cell where the gases are collected separately and can then be used for various applications such as fuel or energy storage. So this process have some advantages. This is a well sustainable technology and commercialized for industrial applications, noble metal-free electrocrystals, and relatively low cost, long-term sustainable. So these are the advantages of this. And this technology is require some improvement. So the thickness of the diaphragm can be reduced with lower resistance that can be improved the cell efficiency and reduce the electricity consumptions. So the lower current density is one of the major barrier to alkaline water electrolysis. This can be achieved by using the thinner diaphragm with high specific surface area electrode material. So uh, typically alkaline water electrolysis take place on high concentrated potassium hydroxide electrolytes and high thickness diaphragm with nickel-based electrode. During the electrochemical reaction, this can allow the intermixing of the generated gases, which are dissolving into the electrolytes substance, subsequently producing the low purity of the gases. Uh, so next is anion exchange membrane AEM process. So this is uh, just that improvement in the alkaline water electrolysis process. So AEM water electrolysis process technology is similar to conventional alkaline water electrolysis. However, the main difference between this alkaline and AM water electrolysis is the replacement of conventional diaphragm with the anion exchange membrane in alkaline. So here, so there is a process is quite similar with the alkaline waters electrolysis. So here the advantage is what? The cost-effective transition material catalyst being used instead of noble metal crystals. And there is a low-cost material means AEM electrolysis use more abundant and less expensive materials for both the membranes and electrodes compared to other method like proton exchange membrane PAM and electrolysis, which typically require precise material. So efficient wise, if we say that the advantage at the low temperature, so AM systems can operate a relatively lower temperature compared to high temperature electrolyzer such as the solid oxide electrolyzer, which we will discuss in the next slides. So making them suitable for a wide range of applications. By using a hydroxide ion instead of protons for conduction, AEM system can potentially offer higher efficiency, especially when coupled with renewable electricity sources. So here, the membrane durability is one of the major challenge to scaling up this technology. The present membrane durability is around 30,000 hours, only due to polymer degradation from the membrane's backbone chain. Therefore, considerable innovations are required to increase durability and overcome to polymer degradations. This can be achieved by increasing the chemical, mechanical, thermal stability of the membrane, along with increasing the ionic conductivity using high conduction polymer compositions. Now, I just go on the next is our PEM water electrolysis. So, polymer membrane electrolysis. This is to overcome the drawback of alkaline water electrolysis. The first PEM water electrolysis phenomena was idealized by groups and developed by General Electrical Company in the year of 1966. However, PEM water electrolysis technology is similar to PEM fuel cells technology. Here, the uh, sulfonated polymer membrane can be used as an electrolyte. Typically, the PEM water electrolysis operation at the lower temperature, 30 to 80 degree, with higher current density and produce high purity of hydrogen and oxygen. It's near to 99.99%. During the PEM water electrolysis process, water is electrically split into hydrogen and oxygen. So how means what is inside this and how it's worked. So proton exchange membrane, that's the PEM, is a solid polymer membrane that conduct protons from anode to cathode, but block electrons entering the electrons flow through the external circuits. So here they ensure that the electrons should be flow through the external circuits, and that's the protons from the anode to cathode only. So electrodes, the two electrodes, anode and cathode, are typically made of platinum or iridium. So platinum or palladium for the cathodes. Power sources, we say that every electrolysis process we require DC, direct current, and it applies to the electrode to drive the electrolysis process reactions. So a reaction occurs where water molecules are reduced to gaining electrons to form of hydrogen gas and protons. So in the SPAM, you can see this at the cathode side. But at the cathode, the water H2 receives electrons from the external power source and the hydrogen gas H2 is produced along with the hydroxide ions. And these hydroxide ions going towards to anode. At the anode side, an oxidation reaction occurs where water molecules are oxidized to form of oxygen gas, protons and electrons. At the anode, water molecules loses electrons and is split into oxygens and protons and electrons. And electrons moving through the external circuits. The model of single cell electrolyzer is supposed to describe several significant processes in the electrolyzers so that it can give precise result. So PEM serve as a separator between anode and cathode. It is the key to the process because it allows protons generated at anode to pass through the cathode side, and it's prevent of mixing of hydrogen and oxygen gases, which could be dangerous. It blocks the flow of electrons, forcing them to travel through an external circuit to maintain the electrochemical balance, creating the electric current that can be used in applications such as fuel cell or energy storage. So benefits of the PEM water electrolysis is so offer several advantages like high operating current density because the kinetic of hydrogen evolution reaction in the PEM water electrolysis is faster than alkaline water electrolysis due to high active area of the material surface of platinum electrode and lower pH of the electrolyte. And second benefit is higher purity of the gases, higher outlet pressure, and smaller footprint due to the absence of caustic electrolytes. Therefore, globally, several water electrolyzer manufacturers are developed large scale up to the megawatt PEM water electrolyzers for industrial and transportation application. However, a major challenges associated with this technology is cost of component like this platinum electrode. Therefore, considerable development are needed to reduce the cost. Now, the last one is this solid oxide electrolysis. The solid oxide water electrolysis cell is the one of the electrochemical conversion cell. It's convert electrical energy into chemical energy. The development of solid oxide water electrolysis was begun in USA in the year of 1970 by General Electric and Brookhaven National Laboratory, followed by Dornier in Germany. The process of SOEC electrolytes operates a higher temperature with the consumption of water in the form of steam and generate green hydrogen and oxygen. During the solid oxide water electrolysis process, initially at the cathode side, the water molecules are split into hydrogen and oxygen by the adding of two electrons. The hydrogen released from cathodic surface and a remaining oxygen ion are travel through the ion exchange membrane to the anode side. At the anode side, the oxide ion are further reduced to generate oxygen and electrons. Then produce oxygen is released from the anode surface. and electrons are traveled through the external circuit to the cathode side by the positive attraction of cathode. Sorry. The process involves two main reactions occurring at the cathode and the anode, facilitated by the solid oxide electrolyte. These two processes happen. At the cathode, negative, which is the negative electrode, the reduction reaction take place where water molecules are reduced by electrons to form hydrogen gas H2 and oxygen ion O2 negative. At the cathode, water is reduced by gaining electrons and producing hydrogen gas and oxygen ions, which then pass through the solid oxide electrolyte to the anode. Now, in the anode side, the oxidation reaction occurs when the oxygen generated at the cathode are transported through the electrolyte to the anode, where they are oxidized to produce oxygen gas. And oxygen ion move through the electrolyte from the cathode to anode, where they are oxidized and releasing the oxygen, and the electrons will be transferred through the external circuits. This is already as we explained. As the electrolytes operate at high temperature, is a 500 to 850 degrees centigrade, can drastically reduce the power consumptions to split the water into the hydrogen and oxygen, consequently increase the energy efficiency. So in this way, this high temperature point of view, this is require less electricity, we can say power. So this improvement in energy efficiency can lead to a strong reduction in hydrogen cost due to the power consumption being a main contributor to the hydrogen production cost in electrolysis. Apart from that, it offers two major advantage compared to the existing electrolysis technologies. The first one is high operating temperature, which result in a favorable thermodynamic and reaction kinetic allow undrilled conversion efficiency. And second one is that it can be thermally integrated easily with downstream chemical synthesis, that is production of methanol, dimethyl ether, and ammonia. So, moreover, the solid oxide water electrolyzer does not require the use of noble metal electrocrystals and give high conversions efficiency. Despite this advantage, insufficient long-term stability has prevented the commercialization. So SOEC is a developing technology with a higher efficiency. However, the main challenging is the durability, and so significant advancement are essential to this area to increase the durability. So this is, and the next slide, here I just specify the characteristics of electrolyzers based on their uh, operating temperature, electrolyte separators, and then the electrodes, anode and cathode side. So here, same things we discuss, and then I just prepare here the tables to give the brief idea about the characteristics of electrolyzers. And the advantage, disadvantage already we discussed. So that's the AWE, this is commercialized, same as the PAM also the commercialized pretty much. And the SOE is partly commercialized, but AEM is not yet. Energy efficiencies is AWE is lesser than all these three. Remaining all these three has the 90% of energy efficiency. Metallurgy's point of view, that's the non-noble metals is used in AWE, and but PAM use the special material, and SOEC is a no-noble material, same as the EM. And the purity point of view, that's the all are highly purified except the AWE. And durability is higher for AWE, that's the commercialized process, and then is a higher durability other as compared to the others. Yes. Now I just go on the hydrogen storage. So sorry, change. Yeah. So hydrogen storage is a critical aspect of hydrogen economy, as it allows hydrogen to be efficiently stored for a later use in various applications such as energy storage, transportations, and industrial process. Due to hydrogen's low volumetric energy density in its gaseous form, effective storage methods are necessary to maximize its potential as a clean energy carrier. So there are several methods for storing hydrogens, each with its own advantages, challenges, and applications. So these methods are typically categorized into physical storage, chemical storage, and storage using physical transportations. So here, there is a means, if we can say, the compressed gas storage, that is the one form we can store, and then liquid hydrogen storage, metal hydride storage, chemical hydrogen storage. So there is some of storage things, way we can store this hydrogen. So compressed gas storage is what? So hydrogen is stored as high pressure gas form, typically at a pressure of 100 to 700 bar in specialized container, such as high strength composite cylinder or steel tank. So this is the way, because in the name there is a clearly specify is a um, high pressure gas storage. So there's a compressed gas storage. So if, when we going to compress, so then we require the we have to maintain some pressures, and for maintaining that pressures we require some special type of cylinders. So advantage is what? Simple and well-established technology, because cylinders normally we use at home also. So in the cylindering technology, we are already in well-established, easier to handle and transport compared to liquid hydrogens, because the other form of the liquid hydrogens this is easier for that as compared to that, and can be used in a wide range of application, including transportations and the hydrogen fuel cells in the vehicles. Nowadays, this hydrogen fuel cells vehicles is going to develop, so there we can use. So challenges also is there. If we are advantage, so we have some challenges in this storing facility. So requires energies to compress this gas. So here challenge is what? Then we have to again require the energy to compress, because we have to produce the hydrogens in the cheapest form. If we require the less, use the less money, so we need to use the less amount of power to generate that. So requires energy to compress the gas. This is the challenge. And second, the high storage pressure leads to material stress and requiring robust, expensive tank. And volumetric energy density is lower compared to liquid hydrogen or the other form of the energy storage. So these are the challenges which we have here in this storing facilities. And application point of view, the transportation and refilling station, we use such kind of storage arrangement. Liquid hydrogen storage. So second form of storing is liquid hydrogen in the form of liquid. So hydrogen is stored as a liquid at a cryogenic temperature around minus 250 degree 53 degree centigrade. This method requires maintaining low temperature using cryogenic tank. Sorry. And because we are just using this technology, so this technology has some advantages. So advantages is high volumetric density than compressed hydrogen, meaning it takes up less space. Stability for large scale storage and transportations. Examples, space missions, larger fuel tankers, like this. And this storage facility also have some challenges, require that the significant energy to liquefy hydrogen at the low temperature re-refrigerations. And the other challenge is boil off losses, where some liquid hydrogen evaporate during storage or for handling. The need of specialized insulated tank capable for maintaining cryogenic temperatures, because to maintain the temperature then require some insulated tanks, that's to maintain the temperature. And the application point of view, this is used for the large scale transportation and heavy duty transports. We use this like that for the larger vehicles such as a truck or ships where greater energy density is needed. So in such places we use these storage techniques. um, Third one is metal hydride storage. So in this method, hydrogen is chemically bonded with metal alloy such as palladium or magnesium to form of metal hydride. So hydrogen can be released from hydride by heating or reducing pressures. So these methods also have the advantages compared to the other. So hydrogen is stored at a lower pressure, making it safer than compressed gas storing method. Can provide a higher volumetric energy density than compressed hydrogen. And solid state storage can be advantageous for a long-term storage and transportation. Excuse me. So here, I also want to explain that the challenges for this storing methods, because this is a very good, but still have some challenges to using in. So high material cost and relatively complex system for changing and charging and discharging hydrogen, because first we have to charge the hydrogen in that particular material form and then discharging the hydrogen from that particular material form. So we require material cost for that, and limited capacity of some materials and releases hydrogen efficiently. So this is also the one challenge, because the material capacity of the some materials to absorb that, how much they can absorb. So that is also the one point, and releasing hydrogen efficiently. So we can release the hydrogen completely from that particular material. So this is the one more challenge. And slow kinetic in the absorption and desorption process. So the application is that the portable storage and the backup power systems for energy storage. Now the last one is hydrogen storage. So hydrogen is stored in the chemical compound, example, ammonia, methane, or liquid organic hydrogen carrier. So this compound can release hydrogen through chemical reaction when needed. So we have to store in this form, and whenever we require, so we can release the hydrogen from the chemical reaction easily. So there are the two types of form that we can store this hydrogen. One is the ammonia, use of the ammonia. So ammonia can be used as hydrogen carrier, where hydrogen is released by cracking the ammonia at high temperatures. And the second one is the liquid organic hydrogen carriers, LOHC. So hydrogen is bounded to organic molecules and released via chemical reaction. So this is the way we just first bound this, and then after that through the chemical reaction we can release this hydrogen. So this is the the two types in the chemical form that we can store hydrogen. And this way, there is some advantage of this storage facility. Hydrogen can be stored in more stable, safer form than gas or liquid hydrogen. So this is the main advantage. And this component are easier to transport and handle, especially over long distance. So these tools are the main advantages of this storing arrangement, but there is some challenge to adopt this storing arrangement. So require chemical processing to extract hydrogen, which may need energy input. Again, we require the energy input to do this extracting the hydrogen from our storing methods. So handling and storing these compounds require specialized infrastructure. So then we require the specialized infrastructure to arranging this. And the application point of view, long distance transportations and exporting hydrogen. So this is the main applications for that particular. So here we can say the key consideration of hydrogen storage. So key consideration of hydrogen storage is what? So energy density point of view, hydrogen has a low volumetric energy density in its natural gaseous form, making efficient storage solution essential for maximize storage capacity. So that's the one key consideration. Second is what? So safety. So hydrogen is highly inflammable and require special precautions during storage to prevent tank leaks, fires, or explosion. And then the cost wise, technology like liquid hydrogen, metal hydrates are more expensive to implement compared to compressed hydrogen, but offer higher energy densities. So that's the point. And the efficiency point of view, the hydrogen store and retrieve must be energy efficient to make the overall hydrogen supply chain competitive with other energy carriers. Infrastructure, many of the more advanced storage methods like pipeline and underground storage require significant upfront infrastructure investment and scalability. So storage technology must be scalable to accommodate varying levels of hydrogen demand for a small scale use to large scale industrial application. So this hydrogen storage, effective hydrogen storage is essential for the success of hydrogen economy. So this is also the main factors, because if we cannot store successfully, so this going toward this transition is slightly difficult. So enabling hydrogen to be stored, transported, and used as a clean energy source. While technology like compressed hydrogen and liquid hydrogen are currently dominate, and innovation in metal hydride chemical carriers and carbon-based materials could be lead to more efficient and safer storage solutions in the future. So there is a more development going on in this side, and in futures maybe we are going to use such kind of storage element. So development of the hydrogen storage technology will play a key role in unlocking the full potential of hydrogen as a clean, sustainable energy carrier. So second is also that if we are storing that, then we require the transportation also. So we have to transport hydrogens gas properly, safely to the industry and wherever is required on that particular place. So transportation is a key challenge and area of focus in the hydrogen economy. So particularly a hydrogen is a vital clean energy carrier because hydrogen is typically produced in one location, such as the large scale industries sites or the renewable energy hub, and consumed in another. Example, fuel cells vehicles or industries facilities where the hydrogen is required effectively. Sorry, effective method of for transporting hydrogen are essential for enabling widespread us use. So there are several methods of hydrogen transportation, each with its own advantages, challenges, and application. The methods can generally be categorized into gas phase transportations, liquid phase transportations, and chemical transportations. So transportation as a compressed hydrogen gas. So that is also is because we have the storing arrangement and the based on the storage. So we have to transport that things. So first is the compressed gas, hydrogen gas, how we can transfer it, the method. The hydrogen is transported at high pressure gas in a cylinder or pipeline. For a transportation purpose, hydrogen is typically compressed to the pressure of 200 to 700 bar, depending on mode of transport. So that is very important, the mode of transport. And the advantages of this transportation is well-established infrastructure for transporting gas via pipelines, because pipeline we normally use, and that's the well-established that because we are uh, transporting crude oils, gases also through this. Direct use in the fuel cell, the compressed gas can be directly supplied to the fuel cells in a vehicle or stationary applications. Low energy requirement compared to liquefying hydrogen. So here also, while we are storing, so same as the in the transportation, we also have some challenges. So energy intensive compressions. The process of the compressing hydrogen requires significant energy, especially for high pressure level. And the second challenge is safety consideration. So high pressure gas require robust storage tank and infrastructure to prevent accident or leak. And limited density. There is a one more challenge. This is the limited density. The hydrogen, even when compressed, has a lower energy density. So compared to the liquid hydrogen or hydrocarbons, meaning more storage volume is needed. And so this second storage was the liquid hydrogen and the transportation as a liquid hydrogen. So how we can transport this liquid hydrogen? Hydrogen can be transported as a cryogenic liquid where it is cooled to temperature below a boiling point of minus 253 degrees, 53 degrees centigrade. So liquid hydrogen has higher volumetric density compared to compressed hydrogen. So making it more efficient for a long distance transport in larger quantities, because we can take more. And the advantages is the higher energy density compared to compressed gas, allowing more hydrogen to store and transport in a given volume. So that's the advantage. And suitable for the long distance transportation, particularly for larger scale shipment by tanker, truck, or ship. Now here this transportations we have some challenges. This like that the in the storage also the cryogenic infrastructure the same things. The specialized tanks and pipelines are required to maintain ultra low temperature and insulation specifically to maintain that temperature. They require the special insulation which increases cost. So energy consumptions. So liquefaction of hydrogen is energy intensive and requires sustainable cooling systems to maintain the low temperature and boil off losses, because there is a chances of the losses while storing and transporting. So over temperature, sorry, the over time, some hydrogens will evaporate or boil off due to the heat absorptions from the surrounding environment. So in applications where we can the international transports, liquid hydrogen is already used for the large scale shipping. For example, from regions where hydrogen is produced to area where it is consumed, and hydrogen exports. So some countries with abundant renewable energy sources like Australia are considering liquid hydrogen for export to countries such as the Japan or Korea. And then the large scale distribution, the truck or ship transport liquid hydrogen to fueling stations or the large industrial facilities. So now the third one is we can say the transportation via hydrogen pipelines. So what is this? The pipelines we already discussed. Method. Hydrogen can be transported via dedicated hydrogen pipeline, either in its gaseous or liquid state. This method is typically used for the large scale transportations over long distance, similar to how natural gas is transported. And the advantages is continuous flow. We can get it through pipelines. Pipelines can transport hydrogen continuously over long distance, reducing transportation cost and infrastructure complexity compared to the truck or rail transports. Efficient for the large scale transports, like the efficiency also is higher. For centralized production hub, hydrogen pipeline are cost effective and renewable for developing hydrogen to industrial or energy customers. So this pipeline also has some challenge. We can say that high initial infrastructure cost, like building a dedicated hydrogen pipeline network, requires significant investment, and hydrogen can cause the material like steel to become brittle, which poses challenges for pipeline integrity. So then we have to choose the specialized material or coating are required to avoid these issues. And regulatory hurdles, because pipelines require substantially regulatory approvals, especially if crossing border or entering densely populated area. So that's the challenges here. And then the application like this industrial supply chain pipeline are often used to supply hydrogen to industrial users, refinery, chemical plants, like this. And large scale transportation pipeline are ideally for region with established hydrogen production and consumptions, where they can deliver hydrogen directly to power plant or refilling stations. Transportation via chemical carrier. So that's the one more method. And hydrogen can be chemically bonded to other molecules such as ammonia, NH3, or the liquid organic hydrogen carriers. So this is we use for the storage also. So same thing we use for the transportation. We use this as a trans. So these molecules can be transported and later cracked or processed to release hydrogen. So uh, the advantages for this is safe and easy transport, because we can take it this and then easily transport it. So these carriers are often more stable and easier to handle than pure hydrogen, reducing safety risk. Using of existing infrastructure, chemical like ammonia are already transported using conventional infrastructure, which can be adopted for hydrogen transport. But here is also some challenge, like energy intensive hydrogen release. This process of extracting hydrogen from these carriers, such as ammonia cracking, require energy, because this is the same thing we discuss in the storage also, which impact efficiency. And then chemical processing, the hydrogen must be separated from the carrier, which adds complexity and the cost to the process. Storage of chemical carriers, some carrier like ammonia require specialized storage conditions, and many present safety risks due to their toxicity. So application is the long distance transportations like the same, and because hydrogen bonded and ammonia or LOHC is an attractive option for international shipping or export of hydrogen. So transporting hydrogen to remote areas, these methods may be useful to transport hydrogen to religious and the lack of hydrogen infrastructures. So, and the last, the transport via solid states means metal hydrates. So hydrogen is stored and transported as a metal hydrate solid alloy that can absorb and release hydrogen gas. So metal hydrates can be transported in solid form and then dehydrogenate to release the hydrogen at the destination. So this also have some advantages like the high energy density. Metal hydrates have the higher volumes energy density than the compressed gas, and safer transportations. They reduce the risk associated with the high pressure gas or cryogenic liquid storage. So here also the challenge is because the cost everywhere is the main challenge. The metal hydride materials are expensive and may require high temperature or the pressure to release hydrogen. Limited scalability, second thing, the challenge. The technology is still under development and is not yet as widely adopted in other methods. So these are the methods and the key considerations we can consider for the hydrogen transportation. That's the energy efficiency, cost, safety, distance and scales, environmental impact, So energy efficiency, like the process comprising liquefying and the chemically binding, hydrogen consumption energy, minimizing energy losses during the transportation is a crucial for ensuring the hydrogen remains a viable energy carrier. So the cost of this is the same that we discuss in the storage point of view. There is also the building infrastructure such as the pipeline and the cryogenic tank to capital investment. The choice of transportation methods often depends on the distance, volume, and infrastructure cost. So, based on this, they decide the storage, means where to keep and then where to transport and what's the cost, where to maintain. So, based on that, we design that the storage and the transportation arrangement. Safety also, the hydrogen is highly flammable and transportation systems must be designed with robust safety standard to prevent leakage, accident, and explosion. Same is the storing key consideration. And distance and skills. The transport method chosen often depends on whether hydrogen is being transported over a short distance and or the long distance. Uh, just just a bit. So one urgent call. I'm getting it. Okay. No, that's okay. Over. And the conclusion way that's hydrogen trans hydrogen transportation is a vital to success of the hydrogen economy, and a combination of method will likely to be used depends on the application and the reason. While compressed hydrogen or liquid hydrogen are currently the most commonly used methods for the short and the long distance transportation, but emerging technologies such as the chemical carrier, metal hydrides could play a significant role in enabling more efficient, safe, and cost effective hydrogen transports in the future. So that's will be we develop more and cost effective point of view, and in future going with that these chemicals and hydrate storage and transportations process. Here, then the next slide, I show that the typical plant configurations means how this hydrogen plant is configured. This is just the flow diagram because here the based on our green hydrogen definitions, we can say that the renewable electricity we require, like that here is the windmills, solar panels we show. So renewable energy, we take it from here and going to our the local substation where utility substation where this power supply to hydro electrolyzer hydroelectrolyzers. Based on that design what we are selecting, and from this electrolyzer generate the hydrogen, and hydrogen generated hydrogen will to be just stored and transport to the and consumers like factories, ships, and the vehicles. So this is a basic flow diagram how green hydrogen is generated and then going towards end consumers. And at the end, I just say that's the good words from Dr. Faith Pirol, Executive Director, International Energy Agency. That's hydrogen is a today enjoying unprecedented moment. The world should not miss this unique chance to make hydrogen as important part of our clean and source energy future. Uh, that's the main. And then before this, if you have any question and ask questions, so then we can discuss. But I had just one more main experience want to share with you. Like I have worked in HVDC platforms that is a part of renewable energy resource. So where it will use, where is the wind farms? So wind farms in my projects, the wind farms are located in a offshore, that is in a sea. So there is a plenty of wind farms, more than 90 and hundreds, and they are connected to the single platforms, because the single wind farms, there is a generator and they just give the supply to the main central HVDC platforms. So what I want to share, there is a one challenge what we experience, I want to share with you. So that is, in that HVDC platforms, we are taking all the power from the respective connected windmills and convert it into the DC power supply and transport to the shore. So because HVDC is a good and low loss transporting or transmitting way. So in that particular case, we face the one things, because while converting from AC to DC, we use thyristors panels, lot of converters, so big converters, and there we face that the uh, electromagnetic interference and harmonics in power supply like this. So for mitigating that, we use that Faraday cage, that the Faraday cage. So that Faraday cage systems law we use over there, and how much and whatever we try, that we reduce the electromagnetic inductions due to that cage. So particular room was there, and there is a plenty of transformer rectifier units over there, and that put it in the one room, and that metallic room we prepare, and that metallic room we will connect it to a cage form. So that is the main challenge, how we can connect as a cage in that particular offshore platforms, that is the unmanned platforms. So that things we do it. So that is a main good challenge I just observed, and I think that I want to share with you. And if you have some more solutions like in this field, because there we tried, and this production, that platforms activity is still ongoing, is not completed. Now maybe in this year end it will be on working. Yes. So next is, if you have any questions, so then we can discuss. I suppose that this is here I just give you very um, overall idea about that the process of green hydrogen generations, means from where we generate it, how the power is required, and then we are just taking that the electrolysis process and then transport, storage, and do it. Yes, I saw one hand, Mr. Kishore Patel. I will try my best to give you answer. I will note down otherwise and then reply you later. Yeah,
Hello, good
yeah.
evening, sir. Sir, my question is that what about the economical comparison between other fuels and this hydrogen?
Economical.
Means hydrogen as a fuel, is it economical than the other that can maybe used in the commercial level?
Yeah,
Is
yeah,
it?
yeah. Correct. Because right now we are using this our traditional way to generate that the fuel power electricity, like that the thermo power plants we have, nuclear power plants we have, and why we are going to the hydrogen and how it's economical. Right now hydrogen is not that much economical. There is a development is ongoing, and they are just trying to reduce the cost of the green hydrogen, because green hydrogen is costlier than the other hydrogens, types of the hydrogen, like that I explained that the gray and blue. So because in the green hydrogens we use that the our renewable energies, and that energies we require as means higher side, and the cost point of view, I am not that much expert, because I am not process licensor for generating this. So it's uh, right now is a 90 to 100. I suppose that I remember that 90 watt, 90 watt requires for the 1 kilogram of hydrogen. But I will check and then revert you.
Okay, sir. So, Sachin ji, thank you
Yeah.
very much. Actually, participants have to appear in a test at 6
Okay.
p.m. online. So
Okay.
I think that is another part on which they are busy. But,
If they have any questions, they can send me the
yes,
email,
yes,
so I will try to reply.
I will communicate you their questions. And thank you very much for this excellent presentation, giving a new dimension to this online FDP. So we will remain in touch, sir. Thank you very much.
Thank you. Thank you. Thank you so much.
So I'm closing the meeting, and now you can. I'm just going to submit the attendance so that you can appear in the assessment.
Okay, so I just stop.
Yes, yes. I'm closing the meeting.
Okay. Okay.
Thank
You.
you, sir. Thank you very much.
Thank you very much. Have a nice day. Bye.